Hello everyone. Welcome back to my channel, where we dive into exciting coding challenges and explore their solutions. Today, we're going to tackle a medium-level problem called Find the Safest Path in a Grid. Imagine you're in a city with thieves scattered around, and you need to find the safest path to reach your destination. Sounds interesting, right? Let's break it down and see how we can solve it. The problem presents us with a grid, where some cells contain thieves, represented by the value 1, and empty cells, represented by the value 0. Our goal is to find the maximum safeness factor, which is the minimum Manhattan distance to the nearest thief for all cells along the path from the top left cell to the bottom right cell. The Manhattan distance, also known as the L1 distance, is the sum of the absolute differences in the x and y coordinates between 2 points. So, what's the core insight here? The key idea is to first calculate the Manhattan distance to the nearest thief for each cell in the grid. Think of it like a heat map, where each cell has a value representing how close it is to the nearest thief. Once we have this heat map, we can explore all possible paths from the top left cell to the bottom right cell and find the maximum safeness factor. It's like navigating through a maze, where we want to avoid the thieves as much as possible. To calculate the Manhattan distance to the nearest thief for each cell, we can use a breadth-first search algorithm, or BFS. We start by initializing the distance values for all cells to infinity, except for the cells containing thieves, which are set to 0. Then, we perform a BFS traversal, updating the distance values for each cell based on the minimum distance to the nearest thief. Once we have the heat map, we can perform a depth-first search, or DFS, to explore all possible paths from the top left cell to the bottom right cell. Let's take a look at the C++ code that implements this solution. We start by defining a class called solution, with a member function called maximum safeness factor, which takes a 2D vector representing the grid as input. We initialize the variables n, max safeness, and dist, which stores the Manhattan distances to the nearest thief for each cell. We also define a QQ to perform the BFS traversal. Inside the nested loops, we check if a cell contains a thief and update the distance value accordingly. We then perform the BFS traversal, updating the distance values for each cell based on the minimum distance to the nearest thief. After that, we define a set called safeness to store the safeness factors encountered during the DFS. We define a recursive function called DFS, which takes the current cell coordinates and the current safeness factor as input. Inside the DFS function, we check if we've reached the bottom right cell and update the safeness set accordingly. We then recursively call the DFS function for all neighboring cells, updating the current safeness factor based on the minimum distance to the nearest thief. Finally, we call the DFS function for the top left cell and return the maximum safeness factor. Now, let's analyze the time and space complexity of this solution. The time complexity is n squared asterisk 4 caret d, where n is the size of the grid and d is the length of the longest path. The space complexity is n squared, where n is the size of the grid. This is because we're storing the Manhattan distances to the nearest thief for each cell, and also using a queue to perform the BFS traversal and a set to store the safeness factors encountered during the DFS. That's it for today's solution, folks. I hope you enjoyed this explanation and gained a deeper understanding of how to find the safest path in a grid. If you have any questions or have a different approach to solving this problem, please share it with us in the comments below. Don't forget to like the video, subscribe, and comment your approach below.